Hi there. In recent videos I tried to measure battery capacity at low discharge current, like for this battery here, which turned out to be rather complicated and required some way to record current and then integrate over time. USB monitors that have this function built in can introduce huge errors because they take their own operating power from the same battery they are supposed to measure, as I explained in another video. Some smart chargers, like this one, can monitor charging and discharging, but they are usually geared for higher currents. As the comments on the videos pointed out, there are some USB monitors with built-in batteries, but then I thought it would be more fun to come up with my own solution, which could also offer more functionality. The other thought was that rather than present a finished item on my channel, I could do a video or a couple of videos as I'm going along. So while I'm hopeful something useful will eventually come out of the experimenting and prototyping, I have no idea yet what the final product will look like. So what I want is basically something like this. 2 channels, one to measure volts and the other one for amps. To limit the design effort, the volt range should be suitable for typical batteries and electronics, say 10 to 20 volts max. The current channel should be able to measure milliamps up to 1 to 2 amps. I don't plan to design a new multimeter here. With volts and amps coming in, we can calculate power and accumulated capacity and energy values. It should be flexible enough to add additional features, for example peak detection and statistics and whatnot. The whole thing should be mains powered to allow long measurements and have a PC connection to record voltage current over time. Let's think a moment about the analog input side. There are 3 ways to do this. The first one on the upper left uses 2 separate ADCs, one for each channel. They can be optimized for their job. The voltage one to measure the relatively large input voltage of say 10 to 20 volts, while the other one needs to measure the voltage drop over a shunt resistor, typically in the range of say 100 to 200 millivolts maximum. The ADCs could be set to measure differential, meaning we could allow positive and negative values. However, there are usually tight limits with respect to common mode voltage differences to ground or VCC the chips can handle, so that feature may be of limited use without adding extra input protection. The second method uses just one ADC that can be switched by the processor to 2 channels. This means we save one ADC, but we can't measure voltage and current exactly at the same time anymore. But we can control the switching to make it so fast that it practically doesn't matter. The third method is similar to the second one, but no longer uses differential inputs. This means we are now restricted to apply the correct polarity at the input and the 2 channels share common ground. This looks restrictive, but in fact is exactly what I could have needed many times in the past. I'm not planning to connect this to AC or signal outputs, so it's unlikely that the volts suddenly change polarity. It would be nice to keep differential inputs on the current channel, so in case we switch between charge and discharge. To help with the decision and to keep costs in a reasonable range, I examined my parts bin and the data sheets. My original idea was to go with an Arduino Nano or similar, or maybe with just one of the AVR controller chips, of which I have quite a lot. I found some discrete ADCs for microchips as well, which unsurprisingly are quite similar to what's integrated in the AVRs. Well, you can see in principle that would work with one of the switch ADC approaches discussed earlier, but there are some drawbacks. The most significant is the limitation of 10 bits and that the range can't be set independently for the channels. I guess one could set it quite low to favor the current channel in picking up the very low shunt voltage drop, and then extend the volts channel using external dividers. but there the low input impedance makes this problematic. So one would probably have to add some kind of buffer amplifier for the volts channel. Since the AVRs with their built-in ADCs are not ideal for this job, I looked at external ADCs. I already have an ADS 1015 in my parts bin. It has an I2C interface, and the ADC internally is 12 bits and supports 2 differential inputs or 4 single inputs. It has a programmable gain amplifier or PGA. As a consequence of the PGA, it has a much higher input impedance than the microchip ADCs. The FS in the datasheet, by the way, stands for full scale. This chip looks very usable. For example, one could set up the PGA for the volts channel to run with the plus minus 6.144 volts and the current channel with 0.256 volts. The high input impedance would allow extending the volt range with a simple divider dead easy without sacrificing accuracy. The only drawback is that the PGA setting would need to be changed every time before switching to that channel because there's one PGA. I looked around the Adafruit website for some other ADC options, and by chance I stumbled on this one, another Texas Instruments chip. The Texas Instruments INA219 chip seems to be tailor-made for what I want to do. It has 2 channels, one to sense volts in 2 programmable ranges from 0 to 16 to 0 to 32 volts, but the chip, by the way, can't handle more than 26 volts. The other channel is for sensing the voltage drop over a shunt resistor in 4 ranges. To show what that means, I added these 2 tables. The top one is for a shunt of 0.1 ohm and the lower one is for one for 0.005 or 5 milliohms. As you can see, that with a 0.1 ohm shunt, the range goes from sub-milliamps all the way to 3.2 amps. For the 5 milliohm shunt, you can measure up to 64 amps plus minus with a resolution of 32 milliamps. The loss column is the needed power rating for the shunt resistor. The current channel is differential, so current reversals are no problem. The voltage channel is not, but I don't think that's a problem for me. The chip can automatically calculate the current if you tell it the shunt resistor value, and it can calculate the power as well. It supports calibration to deal with tolerances in the shunt resistor value, and the measurement accuracy is an impressive 0.5%. This chip sounded so interesting that I decided to buy one from Adafruit to experiment with. It comes as a little kit with a ready PCB, 6 pin headers and a 2-wire terminal block. It has a 0.1 ohm shunt on board and solder pads to change the default I2C address of hex 40. Soldering the pin headers and terminal block onto the PCB takes just a few minutes. This is Adafruit's schematic of the board. There isn't much here besides the chip itself. 2 10K pull-down resistors for the I2C address selection and a decoupling cap, the shunt resistor, and 2 10K pull-up resistors for the I2C bus lines. The chip itself is the B version, which is the one with the 0.5% accuracy and more accurate than the A variant. And finally, my experimentation setup. On the upper right, you see a diagram from the datasheet explaining how the INA219 is supposed to be wired up. My interpretation is shown here on the left. There's an independent power circuit with my lab power supply and a load, which happens to be a 220 ohm resistor with a red LED in series. Despite that puny load at the moment, this could be a high current circuit, which is why I show rather thick wires in this diagram. I inserted my Solartron 7150 plus bench multimeter into the circuit to compare the power readings, but I forgot to show it here. The INA219 is connected with thin leads shown here. A couple of things are important. The voltage channel, called V-bus in INA terms, is measured between ground and the V-in- connection. In other words, after the shunt. So V-bus, the voltage, is the one seen by the load. If you want the voltage of the power supply, you need to add V-shunt to V-bus. This also means the automatic power calculation in a chip is not including the power lost in the shunt, but again, this can be easily calculated by the controlling processor. The Adafruit INA219 is connected to a spare Raspberry Pi Zero board. Raspberry Pis and Python 3 are my preferred development environment if I have a choice, so why not? Of course, other environments are available and equally good. For the initial experimentation, I connected the Raspberry Pi using the latest Raspbian Stretch via the built-in Wi-Fi to my PC and used VNC to have a remote desktop. For the first test, I copied a sample program from a guy called Chris Boyle, who wrote a Python library specifically for this Adafruit board called Pi INA219. Of course, it needs to be installed before I can run test programs like this. Now that it's done, let's run it. It shows mostly 0 and some stray voltages, because I had not turned the test load LED on. Let's do that now. The power is set to 5.3 volts and current limit is set to 55 milliamps, but power is not turned on. Now power is on, the actual current is between 15 and 16 milliamps. The 7150 Plus is wired into the test circuit to read the exact current, 15.87. Running the test again shows reasonable values, 5.312 volts and current of about 15.805 milliamps. So how does this program look like? It's just 20 lines and straightforward. The only config value passed into the function is the shunt register of 0.1 ohm and the rest is all default. Let's do another test with a bit more current. I'm going to short the LED and resistor using the white wire. This causes the current limit set to 55 milliamps to trigger and the voltage to collapse to a few millivolts. The 7150 Plus confirms about 53 milliamps. And another test run confirms the low bus voltage and the current of 53 milliamps. So this seems to be working. In these examples, I used the INA219 Python library called Pi INA219. For more information, please check the website shown here. This library is very easy to use. You have seen how few lines it takes to set up and read the chip. Although developed for the Adafruit INA219 board, which comes with a built-in 0.1 ohm shunt resistor, as you have seen, it does allow for different shunts in case you want to replace the resistor with something else, for example, to measure higher or lower currents. It has a very nice auto range feature where the library automatically adjusts the range to always give the best possible resolution. But you can also do manual range, and if an overflow occurs, the library raises an exception. The main feature is probably that it takes care of the convoluted setup required by the chip, but more about that in a moment. There are some drawbacks. Some modes are not yet supported, but the main one is you can't tweak the calibration to accommodate real-world differences from theoretical values. There are two values that need to be set to make the chip work fully to spec. They are the configuration register and the calibration register. The configuration is dead easy. There are different modes which I gloss over for a moment, but the rest is simply setting if you want the 16 or 30 volt range for bus voltage and which of the four ranges for shunt voltage you want and how much averaging you need for bus and shunt voltage measurements. The chip has sensible defaults on power on for this configuration to work without setting either the configuration or the calibration register. But you only get bus voltage and shunt voltage and no current or power, as these will always read 0. Of course, you could just read bus and shunt voltages and calculate everything yourself, but if you set the right number in the calibration register, the chip does it for you. So calibration is really a bit misleading for this. This register simply makes the rest of the chip work, so it isn't really calibrating anything, but it can additionally do that as well. The only problem is that Texas Instruments makes this such a convoluted process that they actually wrote a utility program to help you. It comes with the evaluation kit CD, but I think you can simply download it as well. I did not bother because the steps are in the datasheet and it can be easily done in a spreadsheet or even, like in the case for the Python INA219 library, in the setup function. However, that library stops at step 8 and does not perform the optional step 9, which uses the actually measured current to correct the cal value produced by steps 1 to 8. I like that the INA219 library allows me to confirm quickly and easily that the chip and setup are working, but I want the capability to do my own calibration to real measured values, and it's also way more fun to talk to the chip directly. So out goes the pre-canned library. The new program is called Test INA and quite a bit longer because it talks to the chip directly over the I2C bus and also still contains some debug lines. First, a last run of the old program to see if things still work. These are the values with the shortened LED. And now the new program. It runs in a 1-second loop. Well, there are some formatting issues, but the shunt voltage is in volts, not millivolts, and it seems to be correct. So is the current, at least ballpark. I need some more tests to see if we need additional calibration. Let's remove the short circuit. Okay, so the bus voltage looks reasonable, and the rest of the values also make sense. Okay, that means I can set up and read the chip directly without needing the INA219 library. Great! This is how the code looks like. Not exactly pretty, but this is just testing the principles for now anyway. We do need the GPIO library to talk on the I2C bus. And these are some definitions of the INA registers and config values. These are just out of the data sheet. The cal val is a list that contains the values I calculated for the 4 different shunt voltage ranges. I'm not sure if it brings anything to go over the details how to calculate this. The data sheet, which you can download from many places, does explain it and has sample calculations. The rest here are just functions to write the configuration and calibration registers, and 4 functions to read the shunt voltage, bus voltage, power and current from the chip. The main body just sets up the chip for a range of 16 volts on the bus and 40 millivolts shunt voltage, which is the settings best for measuring the lowest current. And then it calls the 4 read functions and prints out the results in a loop that's kind of delayed by 1 second between each pass. So here's what I'm planning to do next. I have an unused monochrome LCD panel with 2 rows of 16 characters, and I'm going to connect this to the Raspberry Pi Zero. I'm planning to use this to display the voltage and current values and maybe eventually a menu system to drive different functions. I'm also adding push buttons to be read by the Raspberry Pi. For now, all I want to use them for is to allow changing range and of bus and shunt voltage configurations in the INA219 on the fly to do some accuracy tests. I have put the code of the 2 Python programs you saw earlier on my GitHub page with some schematics if you want to follow along. The link to the GitHub page is in the description of the video. This video was possibly a little heavy on the datasheets and the like. I hope the next one is a bit more practical. Please leave comments if you think I should spend more time explaining the calibration calculations or any other part of the code or setup. Thanks for watching.